let me introduce the speaker with his biography. So, Paulo De Morais was full professor of physics at University of Brasilia up to 213. Appointed as emeritus professor, appointed as guest professor at University of Science and Technology, China, visiting professor at Huazhong University of Science and Technology, China. So he has a lot of positions in China, Brazil, and he is a member of European Net Nanoscience Committee, member of IEEE Magnetic Society Technical Committee, senior member of IEEE Society. So I invite Dr. Paulo Cesar De Morais to share his presentation. The presentation, yes, the title is Modulating Magnetic Behavior of Ultrafine ferrite nanoparticles by Surface Coating Thickness.
Acknowledging the organizers of this meeting for the nice invitation to present my talk. And also, I wish to welcome all of you online attending the conference and attending my talk. So today, I'm going to present you how the surface coating of nanoparticles can change the properties of the nanomaterial. In particular, I'll be talking about the magnetic behavior of ultrafine cobalt ferrite nanoparticles. Here is the agenda for my agenda for my talk. I briefly will comment about the cobalt ferrite nanoplatform. Then I will describe how the material was synthesized and how the surface coating with different amino acids were performed. Then I will show some characterization of the end material in terms of structure and morphology. And finally, I will come to the main topic of my talk, which is the magnetic properties of the surface-coated cobalt ferrite nanoparticles. And then a model picture to understand the properties will be presented. My talk will finish with some important points that I want to emphasize. So in this slide, I want to point out some important properties of this nanoplatform comprising cobalt ferrite nanoparticles. So actually, cobalt ferrite is a very interesting member of this family, which has a very high coercive field, a large magnetic moment, and a very impressive biocompatibility. In terms of applications using the properties of cobalt ferrite, we can emphasize the application in spintronics and recording media, in constructing permanent magnet. But in terms of biocompatibility of the cobalt ferrite nanomaterials, it is important to emphasize the use of this material in magnetic hyperthermia, in drug delivery, and also in contrast agent for magnetic resonance imaging. So just to show how the cobalt ferrite nanoparticles are biocompatible. We can show this experiment where cobalt ferrite coated with citric acid and also coated with polyethylene glycol cationic cobalt ferrite magnetoliposomes, when injected in animal model, here is a mice, how the magnetic nanoparticles were observed uh, in the liver of the animal. So this has to do with the biodistribution. And on the left-hand side, you can see the dark spots are magnetic nanoparticles in inside the coffer cells. And on the right-hand side, we can see the magnetoliposomes containing the cobalt ferrite nanoparticles inside the capillary. So there is no reaction. There is no animal reaction or organ liver reaction against the magnet nanoparticles. This is a strong indication of the high biocompatibility of this nanomaterial. In this slide, briefly, I will comment about the synthesis of magnetic nanoparticles, so cobalt ferrite nanoparticles. The synthesis is related to the alkaline co-precipitation of cobalt and iron salts in aqueous solution at very high pH. So it's alkaline co-precipitation at about 100 degrees centigrade. So this co-precipitation produces the magnetic nanoparticles, and it is actually negatively charged. And then we can add some nitric acid and then lower the pH in such a way that the surface now of the nanoparticles is positively charged. And at this point, we have two options. So we can take, increasing the pH, we can take the nanoparticles at the point of zero charge, PZC, and later on you can, again, lower the pH and produce the positively charged nanoparticles. But this route is unstable. So to make the nanoparticles stable, we have to go through a different pathway. So here is it. So you can treat the freshly precipitated at magnet nanoparticles at low pH, and then you boil or you perform a hydrothermal treatment with iron nitride at 100 C for a few hours, and then you end up with a sort of core shell nanoparticle. The core is the preserved structure of the cobalt ferrite, and the shell is actually an iron oxide, mostly magamite. And then we can take, increasing the pH, we can go through the point of zero charge, and then lower the pH again. We come finally with a very stable core shell structure, and the core is the cobalt ferrite phase, and the shell is the magamite phase. This slide shows how the surface coating of the freshly precipitated cobalt ferrite nanoparticles can be performed. So we do the surface coating at different pH, and actually we can track the surface grafting of the coating using optical measurements. Actually, we look at the absorbance, and then we can find the highest absorption regarding the carboxylate group, looking at the asymmetric and symmetric vibrations of the carboxylate. So the highest intensity in absorbance indicates the best pH to be performed the surface coating. So here is one of the amino acids, the glycine. So the cobalt ferrite nanoparticles is coated with glycine, and actually the best pH to perform this coating was exactly pH 5, which gives the best surface coating of the nanoparticles. This slide shows a collection of amino acids that were used to perform the surface coating. So if you look at the structure in the slide, you can see glycine is the amino acid with only 2 carbons in the structure. Alanine has 3 carbons in the structure. And aminobutanoic acid has 4 carbons in the structure. And in the middle of this slide, the aminohexanoic acid has 6 carbons in the structure. And finally, the longest carbon chain is found in the aminododecanoic acid, which has 12 carbons in the chain. So this shows you an increasing thickness of the surface coating. This slide shows the crystal structure of the core nanoparticles. So the X-ray data showing that the core of the precipitated nanoparticles is exactly the expected structure of cobalt ferrite. So we recorded X-ray data from all of the samples with different surface coating, and they show the same X-ray spectra, meaning that the core phase is preserved in the process of surface coating. This slide shows the transmission electron microscopy and the high resolution transmission electron microscopy of the as precipitated nanoparticles. So from this micrographs, we can extract the particle size distribution, which is presented here on the right-hand side. There is the histogram. The vertical bars are the histogram, and the solid red line is the best fitting of this histogram using the log normal distribution function. And this is in particular the uncoated cobalt ferrite nanoparticles. So it's exactly the core of the nanoparticles. And on the lower part of my slide, you can see a collection of particle size, mean size, and size dispersity. So this has to do with a synthesis, typical synthesis, and we can see that the data extracted from the TEM and curve fitted using the log normal distribution provides about the same size of the core regardless the surface coating, and about the same particle size distribution. So this is a very important point, meaning that the surface coating does preserve the core of the nanoparticles in terms of crystal structure and in terms of mean size. This slide shows typical magnetic properties of the uncoated and surface-coated cobalt ferrite nanoparticles. So it shows the hysteresis cycle at 400 K. On the left-hand side is the uncoated nanoparticles, which means exactly the core of cobalt ferrite. On the right-hand side, we have the hysteresis cycle, also at 400 K, recorded from the sample which was surface coated with the shortest amino acid, which is the glycine. So points here in the plot, in the main plot, are experimental data, and the solid red line going to the magnetization is the best fitting of the data using the model picture for superparamagnetism, which is represented by the equation in the lower part of my slide. The first term is just the diamagnetic component, and the second term is the contribution of superparamagnetism. So you can see here L is the Langevin function, and F is the particle size distribution described by the log normal. So from the fitting of both curves, you can extract the particle size distribution. In the insets, you can see the solid red line are the particle size distribution extracted from the fitting of the magnetic data. This slide shows the saturation magnetization of all samples as a function of the temperature between about 400 K up to 400 K, from 4K to 400 K. So you can see a systematic reduction of the saturation magnetization. And besides this trend, common trend, we can see the highest saturation magnetization comes with the from the uncoated nanoparticles, and then a little bit lower is the saturation magnetization with the shortest carbon structure as a surface coating. And then as you increase the number of carbons in the surface coating, the saturation magnetization, it systematically reduces at all the temperatures we have analyzed. So all these curves can be curve fitted with the standard block type law, which has the normalized saturation magnetization goes with the temperature, and there is a exponent beta you can extract from the fitting. So again, symbols in the plot are experimental data, and the solid lines are the best curve fitting using the block type law equation. The table in the lower part of the slide collects the saturation magnetization, the B coefficient, and the beta exponent. You can see all the beta exponent are about the same, around 2.1. The coefficient, the B coefficient, it systematically increases as the number of carbons in the chain increases, and the saturation magnetization actually reduces systematically as we increase the number of carbons in the surface coating molecule. So glycine has only 2 carbons, aminobutanoic 4 carbons, and aminododecanoic 12 carbons. So this slide just present to you what was the model picture to understand the magnetic data. As you surface coating cobalt ferrite nanoparticles with increasing size of the surface coating molecule. So the understanding of the magnetic properties has to do with the particle-particle interaction. In this regard, we have two contributions. The exchange contribution, which is typically a short-range particle-particle interaction, and therefore should be coating independent. And the second contribution is the magnetic dipole-dipole interaction, which is typically a long-range interaction. And that depends on the coating thickness, exactly the way we see the data. We saw that the saturation magnetization systematically reduces as the number of carbons in the chain of the surface coating species increases. And that is due to the dipole-dipole interaction, which is typically the long-range interaction. Finally, I come to some important points that I collected for this talk. So the first point is successful synthesis of core shell cobalt ferrite nanoparticles. Importantly, this is a synthesis protocol that preserves the core phase. Second, it is visible that the shell thickness in the surface coating modulates the physical properties. I presented to you the magnetic properties. Third, the hysteresis curves at around 400 K for all samples. It is explained by the superparamagnetism of all samples. Fourth, the magnetization actually does not saturate below 100 K, even at a very high field of 30 kilohertz. And finally, the strong particle-particle interaction is assumed to dominate the magnetic properties, even at low temperature. Finally, I want to thank the organizers of this global event on material science and engineering. And also, I'd like to acknowledge my main affiliation, which is the Catholic University of Brasilia, and my second affiliation, which is the University of Brasilia. For those who want to contact me and talk more, a little bit more about my presentation, here is my email address. Again, thank you for attending the meeting and attending my talk.